Short introduction about myself. Currently, I'm working in Huawei, the Toronto office. I'm the team lead for the MindData sub-team. So basically, we're a group of around 8 people. And we work on the data pre-processing aspect in MindSpore. So what is MindSpore? So MindSpore is a deep learning platform that is a competitor to TensorFlow and PyTorch. I think those two names are probably something that people are more familiar with. But I kind of wanted to present the perspective from MindSpore and how we're solving the deep learning problem. And today we're going to really talk about MindData. To start off, I'm going to give kind of a brief overview of the problem that we're trying to solve. So for those of you who are new to AI, it's not a big deal. This presentation is really introductory. Typically, when we talk about deep learning, there is an end goal. You want to train a model to do something, be it to recognize sentences and interpret its meaning, or in the simpler cases, like the one that's being shown here, we do something called image classification. So what are we trying to do? We take, say, pictures of cats, and we feed it to a training model through the training process. And what do we want is that whenever we give a sequence of images, we want the trained model to tell us whether or not a cat exists in the images that are being passed in. So typically, it's split up into 2 parts. You'd have the training process and you have the inference. And typically, training takes a long time because you go through a fairly large data set. It's also computationally expensive. Whereas for inference, you really don't need all that many images. Basically, you'd have to give an example, you have a 9-to-1 ratio between the amount of data you have in your training data set versus your inference data set. To put that into perspective, you have like 100 images in total. 90 of those images would go through the training process, and you'd use the remaining 10 to validate your results. And if the results are good, then you have a good model, and you're pretty successful in training it. So here we take a nice living picture of a kitty, and let's say we pass it through training. And for the inference data set, you have something that doesn't look like the kitty at all. So obviously, it probably won't recognize that this is a cat. It was my best attempt at drawing a cat. So sounds like a pretty simple process. But when we take this idea and we extrapolate it to something of a higher magnitude, the process, you start to encounter bottlenecks and problems. So here I listed some of the common ones and why they might happen. So the first one is something that you probably heard of looking at AI in general, is that training can be very expensive and can be very slow. In the case of images, probably training could take anywhere between 4 to 8 hours, depending on your hardware setup. In the case of a language model, if you were to retrain, say, BERT, the process is very expensive and can take up anywhere between 1 to 2 weeks for you to train the model properly. And why is it slow? The reason is, if you took the cat example that we just talked about, and we took the 90 pictures and we passed them through the training process, we don't only pass through the 90 images once. In fact, many times you're training over different epochs of the same data set. So what does one epoch mean? So one epoch is basically 90 images in the training data set, going through it once. So as you can see, when you take that same data set and you go over it again and again, and you train, say, like 80 epochs, Now, that's significant amount of data that passes through your training network. And furthermore, some specific operators can be very costly. So if we took 80 epochs filled with 90 images, you're basically decoding the same image, 70 to 100 times, right? And decoding can be very expensive. Same with some of the Gaussian calculations that are done as part of the training model. So that's kind of the reason why it's slow. And typically, what MindSpore does to kind of combat and accelerate this process is by using hardware acceleration. So we know that we keep talking about training on GPUs because GPUs do matrix calculation a lot faster than CPU. That's one method that MindSpore employs. More on this later when we talk about kind of more of the MindSpore design. But that's one of the things that we do. Next is through optimizing the computation graph. So some of the more expensive operators can be combined, and some can be optimized completely away by having an equivalent implementation of that operator within the graph itself. So by optimizing the computation graph, we're able to get significant improvements over the amount of computation that we have to do when we go through the training process. And finally, there's this concept called minimizing inter-device communication. So what does that mean? Essentially, when we use hardware acceleration and we pass some data to the hardware for computation, we have to get some feedback over a period of time from that hardware device so as to update the model periodically. Now, the longer the period, obviously the less communication overhead. And you probably don't want to have one update to the model per every image. So that's an optimization that's also been employed within the MindSpore solution. So the key, to kind of summarize the key keywords here, keep note that one epoch means that you go over the entire data set once, and that we basically speak of and quantify the processing of images or data through this term operators. So you kind of say, I do a decode on the data, and that's a decode operator. So that's the first pain point. Training can be very slow and expensive, so we want to get the most optimization that we can. The next issue is a bit more tricky. So insufficient accuracy can result from many, many different reasons. And today, it's still an area where active research is being pursued on a day-to-day basis. And the reason is we don't really know what the model is picking up. And we're gradually starting to understand better what the model is doing once we train enough of them. We understand some aspects that may affect accuracy. But in reality, we're still not quite there yet. A lot of the networks that we see today have around 80 to 90% accuracy, and that's considered sufficient. But it's not foolproof. There's definitely still that 10 to 20% that's lacking oftentimes in a model. And if the end result of training differs by, say, 1 or 2%, that could be a make or break deal for the businesses trying to employ the AI model, because that 1 or 2% really at some point turns into business value. So we really want to maximize the accuracy of these models. And one major factor that we found in tuning these networks is that some of the transformations or operators, they kind of behave differently depending on implementation. And as such, we kind of have to dig through, what implementation of the operator gives us the best accuracy. Many of this has already been done. So papers have been written on custom operators that are added to the network that drastically improve accuracy. And if you found one such operator, you could probably write a paper and publish it. on one of the top tier conferences. But that's only one aspect. In the reality of the case is you could have a bad model for your use case. You could be not feeding the proper data, or even the sequence of the data that's being fed into the model can have an impact on accuracy. One example of this is that if we take one epoch of data and we don't shuffle it before putting it into training, the model itself is actually capable of picking up patterns in the sequence of data that is being fed. So that's the level of sensitivity we're talking about here. And all that we can do is to ensure that our operators, when we implement them, give better nominal accuracy than the original paper that was written. So that's we can say that some of these operators behave in the way that you expect them to in a machine learning scenario. That takes us to the third pain point of people using a deep learning model to kind of train their use case, is that the API can be very complicated. And why is that? I talked about different implementations of the operators. And it turns out that for different use cases, you're going to have different options. Your resize could work on both the image and bounding box. It could have different interpolation settings, and they all give you a different output, and they all kind of affect accuracy. So for the simple-minded user who's kind of beginning to learn AI, you really don't know what all of the options do, and that's hard. So when we go and design our API for the user, we try to keep it as simple as possible. And really, we try to make sure that we don't confuse the user with too many options. And really, if the user has a specific requirement, there are other ways of presenting their custom resize within MindSpore. So this is a problem, and I think to give you an example, TensorFlow has been under fire for having very, very complicated APIs, offering too many granular options to the user, and to the point where it's confusing. So fortunately, within MindSpore, we try to avoid this scenario. Okay, so those are the main pain points. But how does that relate to data? What do we mean when we talk about data pre-processing in MindSpore? So that kind of leads us to introducing kind of the MindSpore framework before kind of answering that question. And so if you look at this diagram, essentially in the front end, we have a whole bunch of APIs. And I guess one thing that's missing here is that within the data processing, there's actually a lot more. It's just here it's not shown in detail. So once you have the data processing, you have something called intermediate representation. We'll get into more about this later in one of the subtopics. But essentially, after you've taken a piece of code from the user and you've stripped it down and you've optimized away all of the excessive computation that you need to do, you finally get to run the training graph and the actual training logic from this graph engine portion. So here it includes all of the logic of executing different graphs on different devices, leveraging the MindSpore backend runtime. And the idea is that you're able to run the training and inference process on all of these devices. And that's kind of the general overview. And today we're mostly talking about the data processing and how data processing sits in each and every one of these layers, and how data processing interacts with the edge devices below. So why is data preprocessing different in the context of MindSpore? So first, I want to separate this concept of a data graph and a training graph. The data graph is something that fetches data from the disk, reads it into memory, does augmentation on it before feeding it into the training graph. So if we think about the actual dependencies of this, the training graph is the component that's responsible for updating the corresponding model throughout the training process. It takes some data, computes a set of output, and outputs a model, right? And updates the model in this case. So it's mostly synchronous, because if you treat this as a black box, you take one piece of data, compute it, and then we output and update the model. But the data graph doesn't actually require this synchronous processing. The data graph could execute purely asynchronously. What does that mean? Is that we could have a pipeline which continuously processes data. And we could have this queue of processed data, and that would be okay. We don't really need to update the data graph on a periodic basis. The data graph can just continuously run. And MindData is basically, oh, that zoomed in a lot. And MindData is basically the, sorry about that, is the component for building, optimizing, and executing the data graph. So we took this concept of a data graph, and we took a bit of, say, user code to take some data and do some computation on it. There are actually a lot that goes behind the background of this concept. And I actually have to talk about the 3 different layers and what they're supposed to be doing. So the first piece is the API level, is the code that the user is interacting with. For example, I could define my own function, and I call it an MS function. So this is a Python example. You take the Python API, and the Python API code gets transcribed into an IR. And IR is more or less a compiler term. It stands for intermediate representation. In layman's terms, it's the logical representation of this piece of code. So you kind of say, I have these intermediate variables. My inputs are X and Y. And this is almost like a compiled code from whatever Python front-end code was provided. And you have this IR. This IR can be depicted in this graph here. So if you try to visualize this IR, it would look something like this. Each individual line would correspond to one of these nodes. And essentially, you just feed it some input, and you give it some output. But that's only the intermediate representation. At this point, this doesn't actually execute any data. So when does data actually flow through this graph? And when do you actually see results? And that's during the runtime. So if we took this example and we say, during runtime, we provide it with data in the form of tensors, which is X and Y, and we pass it through a tensor operation, we get some output result. In this case, data that's being computed in the graph exists in the form of tensors. And only when we see the tensors, only at this point do we consider this a runtime. And the distinction is and we have to make this distinction because they kind of have different responsibilities within this process. The user interacts with the API. The IR is the one that gets optimized on. And finally, when the IR is run with actual data, that's when you see the runtime. And going back to MindData, MindData basically gives you all 3 layers, but only for the data graph. So we're looking at something that takes an API, transcribe it into IR form. And finally, when you're running through the data graph, when you're actually executing the data graph, gives you the corresponding runtime and generate the data that you want. Let's look at this in action by going through an example of how this is done here. So say, for example, we're running the data graph already, and we treat MindData as a black box. MindData now just basically provides data to different computation devices. So you have to send data to edge devices like GPU and Huawei's custom chipset called Ascend. And you do that through something called a device queue. Essentially, once we're generating data, we have to be able to send that data to the multiple computing devices. And for non-host, we have a design called something. We have a design which is called the device queue, and we continuously feed data to that queue, so that that data would get fed directly to the edge device, and the computation result will be collected by the MindSpore backend layer. In this case, it's worth mentioning that for Android, this process is a little bit different, mostly because for Android, we're mostly returning the data directly to the host CPU, and we let the backend decide how to execute the different computing operators and on which platform. So that's our requirement. We have to be able to send data to all of these devices from the perspective of MindData. And finally, I talk about the third constraint and kind of a challenge actually for us to exist within this large framework, is that we actually have different shared objects that are being compiled, and we have to define ownership. So in this example, we kind of take a user-side script, an API level script, and this is in Python. So you would import the different MindSpore libraries. And what's actually happening underneath the hood is that once you call this line, you're actually importing a shared object in C++. And when you call the next line, which is the MindData portion, you're actually importing our shared object. And underneath the hood, we actually have to share multiple resources between the different shared objects. Some of the resources include, the tensor definition, the logging service, and in Python, there's something called a Python interpreter. That's also another shared resource that we have to handle. And why is it this difficult from a design perspective is that we have to define specific ownership for each and every object within this script. So it's not as simple as just importing the two SOs. You actually have to define who owns the Python main process and who is in charge of deallocating the shared resources once the training process ends. So that's a further constraint for MindData. Just kind of keep that in mind. Going back to the large picture, we're defining the data processing problem within the MindSpore network and why it's challenging. Essentially, we want to execute asynchronously is the first idea. We have to conform to this idea of API, IR, and runtime for more than one reason. We'll go into more details about this. We have to be able to send data to different computing devices over the course of training. And finally, we have to do that while sharing the same resources as the main back-end runtime of MindSpore. Okay, so now that's most of the background and requirements out of the way, we can finally talk about what our design is and how we designed the data pre-processing part of MindSpore. The requirements are pretty simple. We want to continuously provide data for training. We want to utilize the resources as much as possible to achieve faster data pre-processing speeds. And the reason for being faster in data pre-processing is because we talked about how training is slow. And the faster that the data pre-processing is means that, overall, the final training would be faster as a result of it. And we took this idea of asynchronous processing and we basically made it a pipeline. So what is a pipeline? You may ask. For those of you who didn't study computer architecture, a pipeline is basically this concept where you could have simultaneously have multiple data being processed at the same time within your framework. Say, look at this picture, for example. If I want to process, I guess, 3 files in sequence, and I want to process them in a pipeline fashion, that would mean that I would take the first file, I would feed it into an image folder, and decode it, and then go on to the next operator. And at the same time, when we go to the next time block, the same would be happening for the next file. And so from time block 2 onwards, you would always have 2 operators operating in parallel on different files at the same time. And the final result is that as you take this pipeline approach a bit deeper, and you take this concept that we can process files in parallel, you're able to ignore the time it takes for one file to be processed. And you kind of, over time, see that since each file is getting processed in parallel, you'd see that the end result to process all of these files is significantly faster than if you were to process each file one by one in a non-pipeline fashion. So that's kind of the idea behind the pipelining of the data graph. But within the pipeline approach, we have a further optimization, which exists in the form of parallel I/O. So if you take this idea for image folder, and image folder is just something that kind of takes a folder filled with images and reads them into memory. That's all it's doing. But the slowest thing about reading files into memory is mostly your bottleneck by the I/O. So in this case, we took a master worker approach, and we're capable of reading 6 files at once. And by parallelizing I/O, you can get significant gain versus if you were just to read each file sequentially. So that's another trick that we did at the I/O level, basically to maximize the disk I/O. And I think this is the most important concept, followed by the pipeline approach. So after we've pipelined our runtime, how does MindData adhere to the various layers that was introduced within MindSpore? So if you recall, I'm talking about the API, IR, and runtime. So at runtime, we basically said that we can parallelize I/O and execute the data graph as a pipeline. But we still have to take in the user-defined logic, and we still have to optimize the different logical representation within the data graph. So within MindData, we have a clear distinction of the roles that each class carry. So for example, in the image folder example, you create an image folder data set at the API level that would be transcribed into an intermediate representation, which we then would call dataset node. And finally, when you actually want to run the data graph, you build the IR and you call an optimizer on the input IR, which gives you the optimized runtime graph. Now, the API class doesn't really do anything. It's very simple. You just create it in Python, for example, and you kind of don't worry about it anymore. For the IR that gets billed, actually has a lot of additional functionality. So in the IR level, let's see if I can trick this a little bit. So at the IR level, an optimizer knows how to take an existing IR and optimize the IR graph to output a optimized IR. And from that IR, you can then build your runtime. The IR also knows how to serialize itself. And at the IR layer, all of this functionality is hidden away from the user. And you might be thinking that, hey, this is a lot of additional effort to go through to define the separate graphs for each layer. So API, IR, and runtime, they're all separate layers. Why is it so complicated? And the reason is, you'll see soon enough, is that this complexity is warranted because we have additional front-end languages that we have to support. And we want to basically hide away as much of the functionality from the following IR and runtime layers as possible so that we don't cluster our API definition. Remember, there was one time where we say that the API itself could be very messy. Well, if there were no existence of the IR layer, it would be even more so. And the key point here is, I think it's true for any design problem in software, is that you want a well-defined response. You want to clearly define the responsibilities of each class and to isolate those responsibilities from other classes and to decouple them. Because in the end, from the user perspective, they don't want to see all of that. And from a code maintenance perspective, you probably don't want to deal with any sort of coupling. So all of that is pretty hand-wavy. How does the IR look, on file? So within MindSpore, we have this functionality where you can take an IR, and we actually store that IR on disk. For us, we store it in JSON format. So here we took that example of image folder and batch. So here's the image folder. And up on top, you'd see actually that's the batch data set. And this is how we output our IR. It's a little bit different from the training graph and its IR. So I've shown kind of the IR output as a sample here. But this difference is because the data graph is much more simpler compared to the training graph. There is no synchronization here. And it's a lot easier for us to serialize user input than it is for the training graph. So that's why we don't adhere to their method of serialization. We have our own. Okay. So that covers the layers of abstraction for MindData. And I think I covered the key takeaways. This is one example where the different levels of abstraction really paid off once we had to support different front-end languages. So if we take a look at this, currently the most used API is probably the Python API. We convert Python objects into C++ through PyBind. But over time, we also have our C++ API, and we probably will have additional APIs like Java and Julia going forward. And this separation of responsibility means that the API classes can remain very simple with basically no responsibilities at all. But they would be parsed into the same IR representation. So basically, by having all of these layers, at the IR level and having them different from the API level means that we could share the same intermediate representation going forward. That saves us a lot of time by constructing additional classes to support different front-end languages. And so that's something that you probably won't see in a typical programming design problem, but it is definitely present here. And at the runtime level, by having the runtime level be its own set of classes, means that the runtime level is very much decoupled from the individual front-end languages. So you could basically mix and match what front-end language you're using and on what platform. So you could run C++ on Linux or Android, or run Python or C++ for Python and Windows, whatever it is you're choosing. I want to talk a little bit about this. This diagram is a little more complicated, so probably won't go into too much detail. I put it here because you'll see that there are other things that are associated with different front-end languages. For Python, you have basically the same corresponding classes as C++. But underneath all of this colored modules, all of the white classes are shared. So essentially, this is an interaction graph between our API level and what's happening behind the scenes at the IR level or even at the runtime level. So this is just one such example. And so this basically concludes kind of the main design decisions that we made in correspondence with the MindSpore problem. So if we take a look at our requirements, we execute asynchronously from the training graph. We have our own data graph here. In terms of the API and IR separation, we have our own definition that corresponds to each individual layer. And finally, for sharing dependencies, we kind of went over how we support different front-end languages using the separation of IR and runtime. So at this point, I think that concludes my brief overview for describing MindData within the context of MindSpore.